As our world continues to grow and develop, both in population and industry, our demand for energy has skyrocketed. Over the past 100 years, the amount of energy we use has increased dramatically, mainly by burning fossil fuels like coal, oil, and natural gas. These energy sources are not only limited in supply, but they also produce large amounts of harmful greenhouse gases, especially carbon dioxide, which contribute to climate change and pollution. Experts believe that if we keep using fossil fuels the way we are now, our global energy consumption could increase by more than half in the coming years. There are two major problems with relying on fossil fuels. First, they are running out. Second, they have serious negative impacts on our health and the environment. Because of these issues, scientists and engineers are working on solutions that can help us move away from fossil fuels. One promising direction is to find materials that can capture harmful greenhouse gases from the air, as well as safely store alternative fuels like hydrogen, methane, and ammonia. Hydrogen stands out as a clean and powerful energy option. It contains a lot of energy for its weight, more than any fossil fuel, and when it is used as a fuel, the only thing it gives off is water vapor. This makes it a great option for reducing pollution and helping us shift to cleaner energy systems. Because of these benefits, hydrogen is seen as a strong candidate for being one of the main energy sources in the future. A typical utility company and others around the world are exploring different ways to store hydrogen safely and efficiently. Today, most hydrogen is stored either as a gas in high-pressure tanks or as a liquid in extremely cold containers. These storage methods are already used in some fuel cell vehicles. However, they come with major challenges, especially when trying to use them in smaller, portable devices. Hydrogen gas is very light, and under normal air pressure, it takes up a lot of space. To store enough of it, you need to use very high pressure, which means heavy and large storage tanks. This is where metal organic frameworks, or MOFs, come in. These are special materials made from metal atoms connected by organic molecules, forming structures with lots of tiny holes and spaces. These pores can trap gases like hydrogen, making it possible to store large amounts of hydrogen in a smaller, lighter space. MOFs are still being studied and developed, but they offer a lot of promise as a future solution for clean and efficient hydrogen storage. Storing hydrogen effectively is one of the biggest challenges when it comes to using it as a clean fuel. One promising way to store hydrogen is by using special materials called metal organic frameworks, or MOFs. These materials have lots of tiny holes and a huge surface area, which makes them very good at holding gases like hydrogen. However, the way hydrogen sticks to these surfaces, called adsorption, is usually based on very weak forces. This means that on its own, the bond between hydrogen and MOFs isn't very strong, and that can limit how much hydrogen the material can store. To improve how hydrogen is stored, scientists have found a method called the hydrogen spillover effect. This process helps hydrogen move more easily from where it is first broken apart to where it will be stored. It starts with a metal catalyst, often made of tiny metal particles, breaking hydrogen gas molecules into individual atoms. These hydrogen atoms then move or spill over onto the surface of the MOF or another porous carbon material. This helps more hydrogen stick to the surface, and it can happen even at normal room temperature. Because of this, the spillover method is more efficient and more practical than other high-energy methods that need extreme conditions. Here's how the process works in simple steps. First, hydrogen molecules come into contact with a metal surface that acts as a catalyst. There, the molecules break apart into hydrogen atoms in a process called catalytic dissociation. Then these atoms move from the metal to the storage surface like the MOF or another porous carbon material. Finally, the hydrogen atoms attach to the surface, and some may even move around the surface, depending on how much energy is needed to do so. The movement of hydrogen atoms isn't always easy. There are energy barriers, think of them like speed bumps that hydrogen atoms must overcome to move from one place to another. The strength of the bond between hydrogen and the surface, like carbon-hydrogen CH bonds, can slow things down. Some surfaces, such as MOFs, also have their own energy barriers that range from low to moderate levels. These barriers must be overcome to allow hydrogen atoms to move and be stored effectively. Researchers are exploring different ways to lower these energy barriers. One method is known as hole doping, which changes the properties of the MOF to make it easier for hydrogen atoms to travel across the surface. By adjusting how the material is built at the atomic level, scientists can improve its ability to store hydrogen. All of this research is helping us better understand how hydrogen can be stored safely and efficiently using advanced materials. While the science behind MOFs and spillover effects may sound complex, the goal is simple: make it easier and cheaper to store clean energy for things like fuel cell cars, power systems, and more. Metal organic frameworks, or MOFs, are unique materials made by combining two important parts, something called a secondary building unit, or SBU for short, and an organic linker. Think of SBUs as the metallic part and linkers as the part made of carbon-based molecules. When you put these two together in different ways, you can create a wide range of MOFs, each with its own structure and properties. This flexibility is what makes MOFs so useful for things like gas storage, separation, and even environmental cleanup. One of the amazing things about MOFs is that you can change their structure simply by adjusting the type of linker or SBU you use. For example, if you make the carbon chain in the linker longer, you can change the size of the pores, tiny holes in the MOF. The size of these pores is important because it affects how much gas the MOF can hold. Even when the linker gets longer or is changed in shape, the MOF can still keep its structure and symmetry, which is crucial for it to function well. Another way scientists improve the performance of MOFs is by modifying the chemical groups attached to the linkers. These changes can help the MOF target specific chemicals or behave differently depending on the environment. By changing either the length of the linker or the arrangement of the SBU's active sites, the internal dimensions of the MOF called unit cell parameters can be adjusted. In some cases, changing the oxidation state of the metal in the SBU can also lead to different behaviors and better performance for specific applications. The SBUs themselves come in a variety of types, with different coordination numbers. This number refers to how many connections a metal atom can make, and it can range widely. Researchers use a technique called post-synthetic modification (PSM) to further enhance MOFs after they are initially made. This technique allows them to add special chemical groups or guest ions that can improve the MOF's ability to conduct protons or carry out other useful tasks. With PSM, scientists can create new and improved MOFs that wouldn't be possible with traditional synthesis methods. The way the linkers are arranged inside the MOF can also shape its overall structure. For instance, scientists have developed a specific type of MOF using a linker known as ZRDMBD, which has been shown to remove toxic mercury ions from water to extremely low and safe levels. In another example, when a compound called ZRCl reacts with a specially designed linker like TPDC, it produces a ZR-based MOF with highly stable and functional pores. These types of MOFs are especially good at keeping their structure while still offering flexibility in how they interact with other substances. There are also MOFs that change from being negatively charged anionic to neutral simply by reacting them with other metal compounds like Qcl and a specific type of linker called TTPM. These reactions not only change the charge of the MOF, but also help increase its surface area and improve how strongly it can attract or bind to other materials. One of the most important reasons why metal organic frameworks, or MOFs, are so popular in hydrogen storage research is because they have extremely high surface areas. This means they have a huge amount of internal space, almost like a microscopic sponge, with lots of places where gas molecules, like hydrogen, can stick or be stored. The more surface area a MOF has, the more hydrogen it can hold. Researchers have found a strong connection between surface area and hydrogen storage ability. The higher the surface area, the more hydrogen can be adsorbed. There's even a general rule that scientists use, known as Chahin's rule. According to this guideline, a MOF can absorb around 1% of its weight in hydrogen for every 500 square meters of surface area per gram of material. That is a helpful way to predict how much hydrogen a material might store just based on its surface area. To increase surface area even more, researchers often use a process called heat treatment. This process helps open up more tiny pores inside the MOF, making it even better at storing hydrogen. Some scientists have also combined MOFs with other materials to boost their performance. For example, by blending a special polymer called PIM1 with a highly porous material called PAF1, researchers were able to dramatically improve the overall surface area. This led to much better hydrogen adsorption results. One test showed that adding just 37.5% PAF1 increased the hydrogen storage of PIM1 by 84%. Computer simulations and lab tests have also helped scientists figure out how much hydrogen different MOFs can store under different conditions. Some MOFs, like MOF519 and MOF520, have been tested at very low and room temperatures to see how much hydrogen they can hold. These materials showed promising results, with one of them achieving over 3% hydrogen storage at higher pressures and low temperatures. A well-known MOF called MOF-5 was shown to store up to 6.8% hydrogen by weight, with a surface area of over 3,500 square meters per gram. Even more impressive results were seen with another MOF, IRMOF20, which showed hydrogen storage of over 9% by weight and 51 grams per liter, meaning it was both lightweight and space efficient. Researchers have also developed new MOFs by using special linkers. These are the parts that connect the metal units in the framework. By using a combination of two different linkers, they created an MOF known as DUT32, which reached a surface area of over 6,400 square meters per gram and could store up to 14.1% hydrogen at low temperatures and high pressure. This is a significant achievement that shows how powerful smart design of materials can be. Another group of MOFs, called NU1101, NU1102, and NU1103, showed outstanding performance in both weight-based and volume-based hydrogen storage tests. These MOFs stored between 43 and 47 grams of hydrogen per liter, and up to 12.6% by weight. These results are a direct result of increasing the internal pore space and adjusting the empty space, or void fraction, within the material. Metal organic frameworks have shown impressive results when used at very low temperatures, especially around 77 Kelvin, which is extremely cold. In fact, they come quite close to meeting the hydrogen storage goals set by the US Department of Energy. But there's a major problem. Keeping things that cold isn't practical for everyday use. Storing hydrogen at such low temperatures would require expensive and complex cooling systems, which makes it unrealistic for common applications like transportation or household energy use. That's why researchers have been exploring how MOFs perform at normal room temperature. At standard temperature and pressure, hydrogen exists as a light gas, and it's hard to contain and store efficiently. But MOFs have a useful property. They tend to hold onto hydrogen better than many other materials because of what is called a high isosteric heat of adsorption. In simpler terms, this means they can trap hydrogen more effectively even when things aren't freezing cold. One way scientists have improved hydrogen storage in MOFs is by adding special substances to them. For example, a catalyst made of platinum and carbon PTC was added to a type of MOF called CuBTC. This change boosted hydrogen storage by 3.5% at room temperature 298 K and a pressure of 20 bars, which is a fairly high pressure level, similar to what might be used in industrial gas tanks. Another study took a different approach. Researchers created MOFs using magnesium and other elements. They made versions like ZIF-8, ZIF-67, and MOF-74, and then infused them with magnesium chloride MgCl. This helped improve the way these MOFs absorbed hydrogen. The magnesium addition also made it easier for the hydrogen to be released later. In fact, one of the magnesium-enhanced MOFs, called MgDOPE-ZIF-67, released hydrogen at a lower temperature than others, around 289 degrees Celsius, which is considered a good result in this field. Even after going through 100 cycles of hydrogen absorption and release, the MgZIF-67 material kept its performance. There's also work being done with a MOF called HKUST1, which is made from copper and has very small pore openings. It's strong enough to withstand temperatures as high as 523 Kelvin. Researchers use this copper MOF as a structure to support another hydrogen storage material called LIB. Normally, LIB starts releasing hydrogen at a high temperature, around 380 degrees Celsius, but when combined with the copper MOF, it began releasing hydrogen at just 60 degrees Celsius. That's a big improvement and shows how combining different materials can lead to better performance. When it comes to using metal organic frameworks MOFs for storing hydrogen, one of the most important things to consider is their stability. Stability means how well a material holds up under different conditions, especially when temperatures and pressures change. If a MOF isn't stable, it can fall apart or lose its crystal structure, especially when the solvent used during its creation is removed. This can make it unreliable for storing hydrogen over time. To create MOFs that are more stable, researchers have found that using metals with high valence, basically metals that can form strong connections with other parts of the MOF, helps a lot. These metals don't easily swap out their parts, which makes the whole structure more solid. When MOFs are built this way, they become much more durable and better suited for storing hydrogen long-term. One of the ways scientists test how stable a MOF is over time is by putting it through something called cryogenic cycling. This just means they expose the material to very cold temperatures again and again to see how well it holds up. To do this, the MOF material is placed in a steel container, which is then inserted into a pressure vessel, essentially a strong tube that can hold gas under high pressure. These tests are done at pressures ranging anywhere from about half an MPa to 10 megapascals. In one study, a type of MOF called MOF-5 was tested through 300 cycles of pressure changes at a very cold temperature of 77 Kelvin. Even after all that, it still held on to 97% of its hydrogen storage ability. That's a strong sign that it's a reliable material. Another important part of testing stability is seeing how well MOFs handle being exposed to other gases that might be present in the environment. These could include things like water vapor H2, hydrogen sulfide H's, or hydrochloric acid HCl. Most of the time, these gases didn't affect the hydrogen storage ability of the MOFs very much. For example, even when exposed to small amounts of H2O and H's, the MOFs kept performing well. Only when HCl was added did the hydrogen storage drop a little from 6% to 5.8% by weight, which is still a small change. When using metal organic frameworks MOFs to store hydrogen, one of the key things to understand is how different materials are added or loaded into them. This loading process plays a big role in how well the MOF performs. The method chosen can change how the catalyst inside the MOF behaves, and it can also affect how stable the MOF stays over time. That is why scientists and engineers put a lot of thought into how they load materials into MOFs. One popular technique is called the wetness impregnation method. In simple terms, this involves soaking the MOF with a liquid that contains the active material you want to add. For example, this method was used to load a special MOF material UiO66 and H on to something called MPC's Rho, resulting in the creation of a new material with well-spread ruthenium Ru particles. These ruthenium sites are important because they help improve how hydrogen interacts with the MOF. Another interesting method avoids using any liquid at all. This is known as the solvent-free loading approach. In this process, the MOF is mixed and ground with the desired material in its dry form. The grinding helps the material blend well into the MOF. This technique can help improve hydrogen storage and is a cleaner, simpler option since no solvents are involved. It is also a way to make nanomaterials extremely tiny particles that can fit snugly inside the MOF's tiny pores. By trapping these small particles inside, MOFs can better hold onto hydrogen. A third strategy involves doping the MOFs with high valence metals. This just means adding metals that have a strong ability to bond with other substances. Doing this improves the way hydrogen sticks to the MOF, which increases the total amount that can be stored. In one case, a material called ZIF8 was loaded with liquid palladium PD nanoparticles. The result? It was able to store about 30% more hydrogen at room temperature than without the added palladium. Each of these methods, wetness impregnation, solvent-free loading, grinding, or metal doping, has its own advantages and drawbacks. Some are better at spreading the active material evenly, while others are easier to carry out or better for large-scale use. Choosing the right loading method depends on what you're trying to achieve, whether that's boosting storage, improving stability, or making the material cheaper to produce. Pristine MOFs, which are metal organic frameworks that haven't been altered or mixed with other substances, have attracted a lot of attention for their unique structure and useful properties. These materials have an incredibly high surface area, meaning there's a lot of space for hydrogen to attach to. They also have porous tiny holes inside them that help trap and hold hydrogen. The size of these pores, along with the material's ability to act as a catalyst, makes pristine MOFs especially interesting for hydrogen storage applications. One of the most exciting things about pristine MOFs is how their metal sites work together to help absorb hydrogen. These metal centers inside the MOF structure play a key role by attracting hydrogen molecules and holding them in place. Because of this cooperative mechanism, scientists have looked closely at a huge number of possible MOF structures to find the best ones for storing hydrogen. In one large computational study, around 500,000 different MOF structures were tested using computer simulations. Among these three, PC and 610, NU100 performed the best in both measurements, showing strong results across different pressure ranges. Scientists found that by increasing things like the volume fraction, pore volume, and surface area per gram, while also carefully controlling the surface area per volume and the pore diameter, they could improve the amount of hydrogen that could be stored and actually used. However, it is important to note that no single MOF was perfect in both areas, volumetric and gravimetric hydrogen storage. This means that a MOF that stores a lot of hydrogen by weight might not necessarily be the best at storing it by volume, and vice versa. Still, UMC M9 and SNU-70 showed a great balance between the two, which is very promising when considering how they could be used in real-world systems. Metal organic frameworks, when these MOFs include metal oxide clusters, they become even more powerful. These clusters help create a solid, repeating structure with pores that remain open and stable over time. This strong and organized structure gives MOFs the ability to store gases like hydrogen effectively. The way hydrogen sticks to the MOF depends a lot on the type of metal used. Some metals allow hydrogen to attach loosely, which is called desorption, while others create stronger bonds in a process known as chemosorption. A great example of how metal centers influence MOFs comes from a study that looked at a MOF made with bismuth, called IEF5. This MOF also included a special chemical compound known as DTTDC, which acted as a type of linker to help move electrical charges. This setup allowed the material to help produce hydrogen by encouraging a flow of charge, showing that the right mix of metal and linker can make a big difference in hydrogen production. In this case, the presence of the ligand molecule that attaches to the metal played a major role in transferring charges and making hydrogen generation more efficient. Another group of researchers took a different approach. They made a MOF called MMOF5-5 and tested it with several metals like vanadium V, hafnium HF, titanium T, and zirconium Zr. Their goal was to see how each metal affected the MOF's ability to store hydrogen. They found that hydrogen tended to stick more strongly to the metal oxide parts of the MOF than to the organic linkers. This means the metal centers were doing most of the work in holding onto the hydrogen. Interestingly, the hydrogen molecules were not only sticking because of chemical bonds, but also because of weaker forces called van der Waals forces. These are gentle attractions that help keep hydrogen in place. In particular, the MOFs made with hafnium and zirconium had relatively high binding energies, meaning they could hold onto hydrogen molecules better. The values for how strongly hydrogen was held called binding energy ranged from about 0.04 to 0.16 electron volts, depending on the metal. These MOFs also had high dipole moments, which is a fancy way of saying their surfaces had strong electrical attractions that helped trap the hydrogen molecules. Doping is a technique where metal ions are added to metal organic frameworks MOFs to improve their ability to store hydrogen. By introducing certain metals into the structure, the MOFs can hold more hydrogen molecules and release them more efficiently when needed. This approach is especially important because it can help overcome some of the natural limits that MOFs have in their raw, or pristine, form. One area of research looks at doping a special type of material called boraphene with metals like lithium Li, sodium Na, and potassium K. These metals interact with hydrogen in different ways, affecting how much hydrogen the material can store. Scientists use computer models called density functional theory (DFT) to predict how these metals will behave when added to boraphene. The results show that lithium-doped boraphene can store a high amount of hydrogen up to nearly 14% by weight in some cases. Sodium-doped boraphene also performs well, although slightly less than lithium, while potassium-doped boraphene is not very effective due to poor hydrogen adsorption. The temperatures at which hydrogen is released from these doped materials fall within a practical range of about 200 to 220 Kelvin, making them suitable for real-world applications. Besides boraphene doping, researchers have also developed composites by combining MOF-5 with a conductive polymer called polyaniline PONY. The PONY is first made into a form called PONY-S, then turned into PONY-Eb through a chemical process called deprotonation. When mixed with MOF-5 in a solvent, these composites show improved properties like a larger surface area and more pores, which are critical for storing hydrogen. In fact, a composite with about 75% PONY-Eb demonstrated the best performance, boasting a very high surface area and pore volume. These characteristics mean that the material has lots of space where hydrogen molecules can be stored effectively. One effective way to make metal organic frameworks, or MOFs, work better for hydrogen storage is by combining them with other materials, creating what are called hybrid MOFs. These hybrids mix the strengths of different substances, like graphene oxide, with MOFs to improve how they store hydrogen. Depending on the materials used, hybrid MOFs can store hydrogen through different processes such as dissociation, chemisorption, or physisorption. These terms describe how hydrogen molecules interact with the material, either by breaking apart, forming chemical bonds, or sticking weakly to the surface. A good example of this hybrid approach is the combination of a MOF called UIO66, which contains zirconium Zr. Materials based on zeolite templated carbons ZTC show great stability and can hold more hydrogen compared to some other combinations. In another hybrid example, scientists used a process called thermal exfoliation to combine zirconium-based MOFs with reduced graphene oxide or GO. This method carefully mixes the two materials without changing the MOF's crystal structure, preserving its key properties while adding the benefits of graphene oxide. One of the reasons MOFs are so promising is their unique three-dimensional structure. They have lots of tiny pores that can trap hydrogen molecules effectively. These pores allow MOFs to hold hydrogen even at normal room temperatures, which is important for real-world use. When hydrogen gas enters these pores, it can even condense or gather inside the material, increasing storage capacity. In addition to their natural ability to store hydrogen, MOFs can be made into 3D printed composites. These specially designed forms help protect the MOFs from moisture, which can sometimes damage materials and reduce their effectiveness. By preventing moisture damage, these composites improve the durability and reliability of MOFs for hydrogen storage. When it comes to using the stored hydrogen, proton exchange membrane PEM fuel cells are an excellent match. PEM fuel cells can convert the hydrogen stored in MOFs directly into electricity, which can then power vehicles or other applications. This integration makes MOFs a strong candidate for supporting the future of clean energy.